Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to introduce Ethan Jackson, who was here a few weeks ago and gave a talk. He comes from very interesting intersection of system engineering and software engineering. It's not unusual for our usual crowd. Welcome, Ethan.
Thank you. Great. So today I'm going to sort of continue where my last presentation left off, which probably some of you didn't see. Basically, last time I introduced model-based design. So I want to really quickly reintroduce model-based design, the way that we work on it, and then go into my area, which is the structural semantics of model-based design. Okay, so the talk will proceed as follows. I'll talk about model-based design a bit, philosophize on it. And then I want to develop what we call the structural semantics of model-based design, which is basically the mathematical way of looking at the structure of models that are used in system design. So to give an intuition, you have, let's say, component-based models, which are sort of like some attributed graphs, for example. There are rules on their construction. There are rules about how you can manipulate them into other models. And so you want to sort of build a formal mechanism for understanding that. And I will first describe this formalization in the abstract sense, and then I want to give an application of it to the tools that are developed at my university, which are a set of domain-specific language tools, including graph transformation language. And I want to show how this formalism can be applied to this tool set, and then we'll be done. Okay, so really quickly, model-based design is all about the construction, manipulation, and analysis of models. We usually talk about them in the context of a domain-specific modeling language, which has two parts to it. The syntax of models, or what we call it structural semantics, and the behavioral semantics of models, what they mean, their interpretation. Just a quick example of this, you can imagine some sort of component-based modeling language where you say that the structure of a model is a set of boxes combined by some lines. Usually these boxes are called components, and these things are called ports or something like this. And then you give this diagram a meaning. So a very simple and precise meaning is you could say that each of these blocks is a function that maps from some n values to some m values on the output. And you can say that these connections are some projection operator that pick a particular value and pass it on to the next block. Okay? And then the meaning of this diagram then is just the composition of all of these little functions. Okay, and we call this a domain-specific language. It has everything you need. It has the structure of models. It has a way to give them meaning. Now you have to be a little careful about the structure. Obviously, there's a lot of work done on the operational semantics, the behavior, but you have to be careful about the structure too. So if you consider these two models here, one with feedback, and you apply the definitions that I just told you, you would discover that this model, the transfer function describing this model, is a function of itself. Okay? So in this particular language, when in the structure you put a cycle, in the semantics you get a fixed point equation that you need to solve. And this may or may not have a solution. And in fact, there's a lot of work you need to do to figure out whether or not this has a solution. And it's because in the structure you allow this cycle. A more dangerous case in this particular example is, let's take a merge where you drive two lines together on the same port. And if you run through the definitions, you get a transfer function here where you actually don't have an operator that defines how to compose the values on these two lines. So you can't get away with, just like you can't get away in traditional programming languages without being precise about the structure. In model-based design, you can't get away with it either. But the interesting thing in the model-based tools is that there are a lot more tools that rely on a precise understanding of structure. So there are the so-called metamodeling tools that allow you to describe a language by drawing a picture. sort of like a grammar, if you will. And a tool can take this metamodel, this picture, and it can generate a modeling tool for you that allows you to construct models under the language that you defined. And clearly, all of these tools depend on the precise meaning of this picture. In traditional languages, you have BNF grammars, this sort of stuff. But these don't really work so well for these sorts of things. But the structural semantics isn't well understood here. On top of this, you have model transformation tools that allow you to manipulate models, to convert models from one language to another. And these work entirely on structure. There are rules about how you take subgraphs or subsets of one model and how you manipulate it to create another model. So these all depend on what exactly you're manipulating, and you need to know precisely what that means. At a higher level, there are structural design space exploration tools. The idea here is that you can describe what good models look like, and a tool will represent a space of all possible good models, and then you can operate on this space. You can say, well, I changed my mind. I think that a good model should have 3 or fewer processors. And then we'll throw out all models that have a structure containing, let's say, more than 3 processors. So you can allow the computer to build for you interesting designs without having to really understand the behavior. And so structural design space exploration is important and also depends on an understanding of this. Okay, so the problem, like I mentioned before, is that this really hasn't been looked at so much in the context of model-based design, even though there are already a lot of tools and support for construction and manipulation of models. The metamodels that you find tend to define non-context-free languages so that the traditional grammars don't really hold so well. For example, you can extend models with arbitrary OCL constraints on how models can be put together, and you can build arbitrarily complicated rules. Also, model structures really don't seem so much like sequential strings. It just doesn't seem like the model you want to use to describe. Then graph transformations, like I said, are defined as a mapping from one set of models to another set of models. And if you want to understand any properties about this transformation, you have to understand these domains. For example, a minimal property you might like to know is that if you transform a model from one language to a model in another language, does that transformation preserve well-formedness? If you have a good model here and you translate it, you get a good model out on the other side. Proving a property like that currently can't be done with existing tools. So you don't really know how good your transformation is. And again, there are design space exploration tools. And a particularly important one is that without a rigorous understanding, the IP that you put in these tools is tied to their existing implementation. So if I go back and you look at a metamodeling language, the way that each of these tools interprets that metamodel defines what you've put in the tool. When that tool changes, if you try to migrate to another one, you're stuck. There's no tool-independent description. Okay, so I want to first look at the notion of a class of models and develop a nice framework for understanding classes of well-formed models in terms of their structure. So if you look at modeling languages, there are sort of 3 things that you need to describe a set of models, to describe the set of models that you're interested in constructing. The first one is that you need a set of modeling concepts. For example, it could be that you have components, and that components have ports, and the ports are connected by edges. So you need a set of fundamental concepts. You need a way to build models from these fundamental concepts. So you can say that components can be connected together. So you need a way to describe how you take these basic constructs and you build up models. And then you need a way of pruning out the ones that are bad. Okay? Now, the way I'm going to proceed by looking at this is to first say, well, what is the best way to define the concepts? And the approach I'm going to use is to take the concepts to be a signature which enumerates a set of function symbols of a particular arity, and these function symbols encode the sort of concepts that you have in your language. Okay? So an example, if we stick with this component-based design, in this system you have inputs and outputs, for example. And to identify an input, you can say, well, an input is really a symbol in signal where you give it a name in this argument. It's a function of arity 1. And the constant that you put in this argument says information that, for example, if the constant you put in this argument is in 1, it says that this in 1 constant is associated with an input signal. Okay? So another one, for example, an import now is a binary function symbol. And it says that a component, some block in this diagram named X, has an input port called Y. Okay? So what you do, you can imagine then that the signature encodes the basic primitives in the modeling language, and this is quite flexible. Let's take this edge from ports to ports. If you look in, let's say, a graph-theoretic framework for this, it's complicated about how do you want to denote ports that are sitting on top of a vertex. But here we just say that, well, a connection is defined with a function of arity 4, where the first argument says the component it sits on, the second argument says the name of the output port, the third argument says the input or the component that it is terminating on, and the fourth argument says the name of the output port. Okay, so it's very easy to sort of capture these concepts as a signature. Why do we want to do this? Because once you have these concepts captured as a signature, there's a very elegant mathematical way to describe all the ways you can use these signatures together, all the possible models that you can build from them. And this is the term algebra. And essentially all the term algebra is, you have an alphabet, sigma, and this alphabet contains names, things you can have in your model. FFT, splitter, phase. Okay? The term algebra contains all the ways that you can put names into function symbols, and then you nest that. Okay? So here, for example, you can see that you have a term here where you have a nesting of another term. So it's all the ways you can stick names into these function symbols, plus all the ways you can nest them. All right? So to be precise, a term algebra is generated by some set of constants, and it has unique readability of functions. This is the precise definition. Okay, so then a set of models is just the power set of the terms. A set of model, or a single model is a set of terms. So the set of all models is the power set of the terms. Okay? So an encoding of this diagram over here, a partial encoding might be a set of terms that looks something like this, where you have primitives in the model that are called FFT, splitter, and phase. You have, again, the input ports, for example. So these are just a collection of terms, and the constants denote distinguished elements in the model.
Number 3 says it's free.
Number 3 says that the image of every function will never give you something in the basic alphabet.
No, this is number 2.
Oh, I'm sorry, number 3.
3.
Oh, yeah, I thought you said, is it free? Yeah, number 3 is unique readability of the terms. So that two terms are equivalent if and only if the two function names are the same.
It's like Herbrand universe.
Yeah, it's like Herbrand universe. Yeah, so this is the absolutely free algebra. Yeah. Okay, so now we have sort of a nice picture about how do we encode concepts and how do we build up all the possible models associated with those set of concepts. Now, not all of these models are good. Some are bad. So we need a mechanism to figure out if you give a set of terms, whether that correlates to a good model or a bad model. The natural way to do this when you have terms is to use a logic, because logic is basically a way of concluding new terms from old ones. So the idea is that you pick a particular logic, which is represented as an inference procedure or a consequence operator, and you write a set of axioms where you can prove whether or not a model is good or bad. That's the idea. Okay, let me make this a little more concrete. Let's say that you wanted a language where you only like models that are fully connected graphs. Okay? Then you might say that this language just has two function symbols, v for a vertex, e of arity 2 for an edge. And then you're going to define some constraints on top of this. And to define constraints, you can extend the signature with some additional function symbols to calculate proofs. You can prove which vertices are transitive, which vertices are reachable from anywhere in the graph, And then finally, is a graph well formed. Okay? So to do this, I'll write a set of axioms that allow me to figure these things out. For example, if I have an edge from x to y, then I conclude that you can transitively get from x to y, of course. This line is a mistake that I forgot to correct. If you were able to prove transitive from x to y, and you have transitive from x to y, and then this should be y to z, then you can conclude that you can transitively get to x from z. If there exists a vertex x, such that for every other vertex in the graph, you can transitively get to that vertex from x, or you can transitively get to x from that vertex, for everyone in the graph, then x is reachable from every vertex in the graph. And then finally, the graph is well formed if every vertex is reachable. Okay, so this set of axioms allows you to prove under a particular consequence operator if a set of terms representing a directed graph meet your criteria for well-formedness. And then you just say, well, a set of terms satisfies my constraints if I can prove the well-formed term for that model. Yeah, question?
I have a question on the previous slide.
Yes.
So does 3 disallow you to create circuits with feedback?
This term here?
Yeah, this constraint.
Oh, so this is more a technical definition that makes sure that if you look at 2 terms that don't have the same information in them, that they don't mean the same thing. So feedback, let's see. Let's see, in this example, we have a board. Okay, yeah. So let's take this directed graph example where you wanted to define, let's say, a loop of feedback. Right? Let's call this V1. Then the model would just contain the term V1, V of V1, and then E for edge of V1, V1. And then this represents a feedback because of how you understood edge. Number 3, I flipped it accidentally. Number 3 says that if you see 2 different terms, let's say you had another vertex here, and you had this. Okay. Number 3 says that these terms are really different from each other because when you look inside of them, they have different arguments. Because if you imagine these as functions on an algebra, these functions could do anything you want. They could equate this term with this term and really be describing the same thing. In the term algebra, you make sure this doesn't happen by adding this constraint. Yeah. Is that? Okay.
So term algebra precedes the derivability relation. So it's just a material on which
Exactly. Right.
How would you change this constraint to actually prevent those models to have feedback loops? I'm just trying to look at those terms.
Oh, how would you prevent a cycle?
Yeah, how would you prevent
okay.
a cycle here?
Yeah, if you wanted to constrain this so that there existed no cycles, yeah, then you would still need this transitive symbol, and once you know transitively what you can.
Okay, got it.
Yeah, then you just find no transitive of the form XX. Yeah. Okay, so now we can be more precise. We call a domain a set of models, or more precisely, it's a structure where we have a signature upsilon for representing the basic concepts. We have a signature upsilon sub c for representing the function symbols that you need to prove well-formedness or malformedness. We have the alphabet sigma, which gives us the distinguishable elements that we can put in models, and the set of constraint axiom C that you use to prove whether or not a model is well-formed or malformed. Okay, the problem here now is that if you have a bunch of domains, you can define these any way you like, and it makes it difficult to figure out how domains are related. So I want to constrain this a little bit and put some special symbols in the constraints so that we can always figure out how we have a general way to decide if a model is well-formed or malformed. Okay, so let's imagine that we categorize two classes of domains. One class where the constraint signature has a symbol well-formed in it. And we say that a model satisfies the constraints if there exists some term in the model such that you can prove well-formed for that term. Okay, so this is a fairly weak notion of well-formedness. But if I say a domain is positive, then this is what I need to check. Okay, and then of course there can be different symbols in these constraints, but in the end you just worry about whether you can derive well-formed of T for some term. A negative domain, you categorize the bad models, and then you prove that a model that you give to it is not bad. Okay, so in a negative domain we add malformed into the constraint signature, and we'll say that a model satisfies the constraints if for all terms in the model you can't prove malformed for that term. Now, I know that Professor Gorovich is waiting to tell me that there should be more because you told me that last time, and he's right. But in fact, these two are enough to define other variants if your logic is, for example, closed under negation. So let's say you wanted a stronger form of a positive domain where a model is well-formed if for every term in the model you can prove that it's well-formed. Then you just use the negative domain definition, and you set malformed of T to be the logical negation of well-formed of T, and you apply the second definition. So you can build other sorts of notions of negative and positive domains depending on the expressiveness of the logic that you use. Okay, so this provides now an abstract way to think about how domains are related to each other. So if you know that all you need to look at is this term well-formed, then if you have two distinct domains and you want to know how they're related to each other, you do it by seeing how models in this domain let you get to this set of terms of the well-formed X. Okay? And basically, I guess in the interest of time, I won't go through this whole thing here unless you want to ask later. But basically, when you know that models are related through this well-formed X term, you can see if two domains are equivalent by checking that for every model in one domain, if you get to well-formed, then you also get to well-formed from the model in the other domain. Okay, so if that always holds for both domains, then they're exactly the same. The important thing is just to note that you can describe the equivalence of domains just in terms of this consequence operator, just in terms of the inference procedure. So once you pick the inference procedure, you have a mechanism now to check this property. Okay, now we have the notion of a domain, and now a model transformation or an interpretation is just a mapping from the sets of models in one domain to the sets of models in another domain. We want to be a little more precise and give a way to actually perform a transformation, to build rules that say how you take substructures in one model and produce substructures in another model. We can also do this using the same logical machinery by saying that a transformation says I want to transform models from one signature to models in another signature using some axioms tau that define the transformation. And basically all you do is that once you have some axioms that tell you how to put things in the output model given things in the input model, is you just get all of the things, you collect up all of the things you can prove under these axioms, and you project this on the terms of the output. You throw away all the things from the input, and that's your transformed model. Okay? So let me show an example to make this a little more concrete. Let's say you want to take the shuffle product of two automata. So just a reminder, the shuffle product, if you have two automata, you take the cross product of the states, and then you distribute the edges about according to a particular rule, and you transform these two automaton into a single one. This is a common example used in model transformation. How do you do this sort of this rule that takes this cross product? Okay, so this is the technical this is the definition you find in the books of a shuffle product here. Q or the Q sub I are the states belonging to automata I, and then this arrow represents the transition relation between states. Okay, so you need to encode the automata as some signatures. This is pretty easy. you have a symbol S1 of X for a state in the first automata, event 1 of X for an input letter in the first automaton, an E1 is an edge or a transition from state X on input A to state X prime. And then you reproduce this for the second one, and you call the union of these two your input alphabet. Now you can represent two automata. And the output signature is very similar, except subscripted with 1, 2 to represent things in the product. Okay? And now you just make your axioms tau to describe terms that you can deduce given terms in the input. So if the input automaton contains an event, an input letter X, then you can conclude that in the output model, it also contains that event X. If the first input automata has a state X, the second one has a state Y, then in the output automaton, you can conclude you have a product state XY. Okay? And the edges are a little more complicated. I won't describe that whole process. But basically, you take the encoding of these two automaton as terms, sets of terms. You run this transformation, which means that you generate all new conclusions you get, and you get this output here. And then you throw away any of the terms that were on the input signature. And in fact, these are the ones you're left with, and they exactly correspond to this here. So it provides a nice way to both. So here, notice that the inference procedure is providing the mechanism to define well-formed models and to translate between models. So it's all sort of kept in the same framework. Now we can finally say what a domain-specific modeling language is. It's a domain, as I described before, and a family of interpretations that are just mappings between domains. And some of these mappings we can define transformationally. Now we can figure out how to describe the notion of metamodeling. So just to review quickly, a metamodel is a diagram where you interpret it and it describes the structures that belong to some language.
Before you go to metamodeling,
yeah.
So how expressive is it?
Well,
the domains that really come up, do they lend themselves to be described in this way?
Yeah, the structures definitely lend themselves to be described in this way. The question of expressiveness gets, the point where it hits you hard is what properties do you want to be able to prove? So if you want to do proofs like this, if you want to prove things like domain equivalence, now it depends on what logic you chose for this consequence operator. If you choose a higher order logic, it will allow you to express lots of domains, but now checking this property may become semi-decidable or undecidable. So it's more what properties do you want to be able to check?
So the logic is the parameter.
Yeah, the logic is the parameter, and you can definitely choose a logic that you will be able to describe any domain you wish, but you pay the price in terms of analysis of the properties of those domains. Yeah. So now, actually, we can describe the notion of metamodeling. Yeah, let me just give this example. Okay, this is a metamodel here in the UML-like language for a simple automata. And let me just remind everybody about how it describes a language. It says that an automaton is made up of several classes: a class called state, a class called transition, and a class called start state, which is a subclass of state. This diamond here represents inheritance. So it says that start state is a state. This loop here with the diamond represents containment. So this actually defines a class of hierarchical automata. It says that inside of a state you can have other states. Okay? This containment here, for example, says that inside of a state you can also have other transitions. And finally, this little circle connecting states and transitions says that a transition is a relation between states. It's an edge in a graph, for example, that can start on a state and end on a state. Okay, and then you can have attributes. I put this clearly when you have a start state, this is an and. So for example, this attribute is it an and state? Do the states inside decompose in an and or an or? You can have triggers, you can have actions. So this diagram, you can see how it would describe the language of the structure of automata. Now, to represent this formally, we now want to combine the two ideas that you have a domain and you have a model transformation. We want to imagine that a metamodeling language is just a special domain that has a transformation on it that transfers models to new domains. Okay? So it's a transformation. So first of all, it's a domain. And secondly, it's a transformation from a model, which is just a set of terms, to a domain, which is two signatures and a set of axioms. We'll fix the alphabet. Okay. Now, there's one technical caveat here is that the definition of a domain involves axioms as variables, and I didn't say how you represent those as terms. So there's one trick that you have to make an intermediate step where you describe how to view domains as models themselves. So you can think of let's say, writing a modeling language where the structures in that language are formulas. And what this language corresponds to is it's a sort of a domain of all domains. It's the structural representation of the way that you define domains. Once you have this, you can then continue with the basic transformation approach and say how you transform a model to the structural representation of a domain, and then you just recover from that the actual definition. Now, what's interesting is that this allows you to address, I don't know, has anybody encountered this notion of a metamodel or metacircularity? Okay, yeah, it's sort of like this fuzzy, it's a fuzzy thing that the idea that if you build a metamodel, you can build a certain metamodel that describes itself. And it sort of sounds like a circular argument, but you can actually be more precise about metacircularity. A metamodeling language can describe itself if there exists some model in it such that when you generate its domain, it's exactly the same domain as the original metamodeling domain. Okay? And then if you pick the right logic, you can actually prove whether these two things are equivalent using the previous mechanism. Okay, so to conclude this part then, the big picture is that you have right now these long tool flows that involve many different languages with many mappings between them. And now what you can view them as is a chain of domains, transformational interpretations, where the domains are generated by interpreting models inside of a metamodeling language. And this whole picture is now unified under the same mathematical framework. So it's now all together. And this can allow you to do sort of interesting things. So you can address this issue, does a transformation map, if you give a transformation a well-formed model on the input, does it map a well-formed model to a well-formed model on the output for always? And you can make proofs of that using this framework. Okay. Maybe I should ask now, are there any questions on that part? Okay. Oh,
so is there any the proof apparatus is external to the models. So when you prove that the universal metamodel is equivalent to itself,
right?
In a sense, do you depend on properties within the model, or?
Yeah. So whether or not this metamodel is dependent on itself, it depends on two things. First, what are the constraints on this domain, and then on the particular details of this transformation. So if this transformation can never take you to a point in this sort of structural representation of domains where you can get to a domain that looks like the metamodeling language, then you don't have this property. But actually, something that's interesting that when I was working on this is it's really not that important of a property to begin with. But if you read specs on metamodeling languages, it's really important. But actually, from a mathematical perspective, I don't think it really matters that much whether or not you have this property. But yeah, to be precise, it depends on the details of this domain, in the details of this transformation.
So this is T sub meta.
Yeah.
Is it partial? Does it take any point in D sub meta to D sub F?
Yes. Yes.
It's total.
It's total, right. Because these transformations are going to be defined much like this. So you can push in any input, and then the question is, what are the consequences that you get? You might get a domain here that is not very meaningful, but it's still something. Yeah. Okay, so now I'm going to completely change gears and describe how you can apply this to existing tools. And the tools that I applied this to are the ones developed at ISIS, which is the generic modeling environment, and the graph rewriting and transformation tool. So basically, GME and GREAT are tools for building metamodels and for generating model editors that let you construct models that conform to the metamodel you defined, and for doing model transformations in a graph-based way. Okay, so the way this is going to work is that first I want to define this tool flow without any implementation in mind. So all I want to tell you precisely is what is the definition of the metamodeling domain, what is the definition of the structural encoding of domains, and how do you make a transformation between the two. And once I tell you that, then I have a tool-independent description that precisely gives the semantics of all of these things. And then the second step is to connect this to an implementation that already exists. And what this does is actually puts a nice formal framework right under the tools without having to redevelop all of these tools, which have been in development for 12 years. So they're pretty sizable tools. Now, the most important parameter in terms of applying this is, this is interesting. Oh, you know something? I think I opened the wrong presentation. Excuse me for one quick second. This is, yes. Okay. Let's go here. Okay, there's a slide I want. I gave you an old version. All right. Okay, so the most important parameter is this consequence operator, the logic that you want to choose. It's the most important in the sense that it affects the expressiveness, but it also affects what you can prove about the languages that you define. So we chose a class of logic that is rather restrictive, but I still think it's fairly expressive. What we chose was acyclic Horn logic extended with some fun stuff. So Horn logic, just to remind everyone, you have exactly one non-negated literal, and it's usually written in implicative normal form, where you have terms with variables conjuncted together, and they imply some term h sub n. By acyclic, it means that you can't find any sequence of clauses such that the head of one clause is in the tail of another, and vice versa. Okay, and we extend it with the ability to equate and disequate variables, so disequality and equality constraints. The disequality constraint is that you can write a term and require that the variables have to be distinct. And then finally, with a sound pseudo-negation, and this is actually rather a big issue, but I won't go into it too much. Basically, what it means is that you can sort of negate a term in the tail, where the interpretation is that this negation holds true if you can't prove the positive under Horn logic. Okay, so there's a lot of details. And then finally, this is not a big theoretical constraint, but it's worth mentioning, that I also have the ability to restrict some terms to finite sets. So if I have a function symbol f, and let's say I only want this symbol to be defined at C1 and C2, where these are some constants, I can restrict this and tell the prover, the theorem prover, if you see f, you can only define it at these two places. Okay, so you can restrict it to some finite terms with some constraints. The nice thing is that the logic is decidable. It's fairly expressive because you have this pseudo-negation. But the downside is this pseudo-negation makes existence proofs intractable. They're decidable, but they're intractable. And it's not closed under negation, which means that we often will use negative domains that rely on this malformedness rule. Okay, so a brief review of metamodeling, I think I don't need to do this now, is that you draw a diagram like this. Hierarchical concepts are ones that contain things. You can look inside of them and they have internal structure. Association concepts are ones that are related by this thing and they show up as edges in a graph. And then a primitive concept is something that doesn't contain anything else. And these may have attributes on top of them. And then in addition, you may add to this metamodel constraints. These are usually done in OCL for historical reasons. I guess OCL was made fairly popular, where these constraints can add additional requirements. So what this constraint says is that you can only have exactly one edge on each of these primitive concepts. Okay, so these can be very complicated and they're fairly nasty to read. So first thing we have to do is break this metamodeling language down and to recover a precise definition of the metamodeling domain. Okay, so the first thing that you have is a class. Okay, simple enough. So to define a class, we'll say that in the metamodeling domain, there's a function symbol called class with arity 1. We'll do a similar thing for classes that are actually associations that show up as edges. We'll add a special function symbol, association class of arity 1. And now that can represent association classes. And of course, the argument in the class is the name. Okay? So for example, here we'll represent state by saying class state, where now state is this name of the class. It's something in the alphabet. Transition, which is an association, we'll say association class transition. And finally, we'll have this notion of a connector. This really isn't necessary, but this is how GME does it, so I reproduce this. But a connector is something that stands in the middle of this association. It has a name, and it has a ternary relation called association end, which says that this connector starts on state and is the source, and it ends on state and is the destination. So in this example, in the automaton example, the transitions always start and end on states. But you can have other languages where the rules are more complicated, that an edge has to start on something of one type and end on something of a different type. So you have the notion of defining what is the source and what is the destination. Okay, and then things get a little more interesting when you want to define the rules about how you can relate things together. So, for example, a containment association is represented by a containment symbol of arity 2, and it goes from a class to a class, or from an association class to a class. So now to capture those constraints, we say that a containment is malformed if it doesn't start on, or if it doesn't end on a class. A containment is malformed if it doesn't start on a class or an association class. So now we're using the Horn logic to describe the rules for putting metamodels together. Okay, and you can do similar rules for all of these things. And what you get is an implementation independent definition of exactly what a metamodel looks like. Okay. There's one caveat here, and I just bring this up because it's sort of interesting. It shows to the weakness of restricting yourself to Horn logic, and this has to do with inheritance cycles. Let's say you want to say that metamodels should not have inheritance cycles. To do that, you need to calculate whether or not there's a cycle. Without recursion in the logic, remember I said it's acyclic. Without recursion, you can't calculate whether or not there's a cycle of arbitrary length. Instead, you approximate it by saying that there's an inheritance cycle of length 1 if you see an inheritance edge from x to x, from class x to itself. There's one of length 2 if you see an inheritance edge from x to y, and x and y are distinct. is 1 of length 3 if you see an inheritance path from x to y to z, and an inheritance edge that extends it by 1, and so on and so forth. So you can encode a finite test, but you're restricted to finite. When you add recursion, then So each time you add it, it makes the theorem proving potentially exponentially more difficult, because you now have an exponentially expanding set of structures that you have to look at. So that's why, if you really want to be able to prove theorems about these languages, you can't add that recursion in. Of course, in Prolog, you do this with lists, or you do this with recursion, and you normally have the closed world assumption that you start with a finite set of terms, so you will terminate. But for these, you don't have the closed world assumption. Yeah.
So it's not possible to extend your logic with a restricted recursion scheme.
No,
I
think it is possible. I haven't looked into it, but I think it's a really interesting question about how could you extend to recursion, because definitely you do want to be able to describe these sorts of properties where essentially you have an infinite number of distinct structures described by a single property. And those are the hard things to represent this way. But yeah, I think that's a really interesting topic. I haven't had time to look into it much yet. But
So where do you use the distinctness or the finite domain restriction? Does it show up on your slides?
The finite domain...
Go back 2 slides.
To this one?
1 more. And 1 more. There.
Oh, okay.
Number 3 on the right. Restrict F to...
Oh, yes. Yeah. In this example here... sorry. Where did I have attributes?
Can you explain the question?
Yeah.
Is there an example where it's used?
Yeah.
Then I'm going to ask another question.
Yeah, okay, let me show you an example. I took it out because, in the interest of space, but I think I have... okay, I'll just tell you. In the case of an attribute, where did I have? I deleted it, but an attribute is something that has a type, an attribute where you say the type of the attribute, and it's restricted to 3 possibilities: Boolean, string, and enumeration.
Great.
And so, when you want to describe an attribute, then what you say is that an attribute is a ternary function symbol, where one of its arguments is a type, but type is restricted to only these 3 constants.
Okay. So, So the finite domain restriction is, by the way, it's motivated by their use.
Right. Because, yeah, so a lot of times
Suppose you had an algebraic data type, a free data type, say list instead of type being list of integers.
Uh-huh.
Or type schema for declaring types. So then you wouldn't have a finite number of instances for it, but each instance would be guarded by either nil or cuts,
Mm-hmm.
where cuts would have variables as arguments. Would that be possible?
Yeah, so basically what you're getting at is that right now I took the approach of lumping all of the data into this sigma, into this single alphabet. And the problem with types like you're saying is that if you wanted to restrict some argument to be an integer, what you want to say is that this has to be a subset of sigma, which is the set of integers, but you can't enumerate that subset because...
You can't enumerate it, but you can describe it.
Right.
And the question is the way that you capture or handle this restriction. Isn't that just a restriction on the unification?
Yeah. I guess there are two questions. One is how does it, so the more important question is how does that extension actually show up in the proving machinery?
Yes.
Yeah. And in terms of what you just described, it would just be a restriction on unification. You're absolutely right.
So the question is that the way you do it? Or?
So right now I haven't extended it to handle restrictions that aren't finite. Because the restriction you just described is a restriction, but it's not a finite one.
Correct, but you did implement, or you have worked out the finite restriction, and the question is where is it manifested in the engine?
Oh, in the actual proving engine.
Yes.
Okay. I'll answer, but if you want more of an answer, we can continue it because it's an involved discussion.
Okay,
I think.
So we'll take it on.
Yeah, but the short answer is that the proving engine uses the open world assumption, which means that it wants to find a model that satisfies some properties. You don't start by giving it a model, but you say, does there exist a well-formed model with such and such properties? And it essentially has to use backwards chaining, but it can't terminate at a set of ground terms. It has to figure out the ground terms. Now, the finite restriction here is that as it's trying to figure out the ground terms, if it hits a function symbol that you restricted, then it can just, in the backwards chaining algorithm, it can just pop out and enumerate the finite number of elements and only have to consider those.
Oh, okay.
So in the case of Z, it can't pop out and examine every model that is filled in with every integer, because you have the open world assumption. Yeah, so it definitely has to be handled carefully, but it's definitely something you'd like to have. Okay, so just to review then, what you can see these slides represent is a tool-independent definition of a metamodeling language. All that you do is define the structure of metamodels. If you have some terms of this signature, you can figure out whether they correspond to a structurally good or structurally bad metamodel. Okay. Now, the way that we implemented this in GME is sort of interesting. GME is, like I said, about 12 years old now and several 100,000 lines of code. And I don't want to try to prove that GME does what I just said in the last couple of slides. That the code actually implements exactly this language. So instead, I take GME, which already has a metamodeling language, and I construct in GME a representation of this simplified metamodeling language I just showed you. Okay, so in this picture here, you have a simplification. You have this metamodeling language I showed you, but described in GME's native metamodeling language. Okay. Now, if you run MetaGME on this, it gives you now a modeling tool for constructing this simplified metamodeling language, and you can construct an example here. Okay, so now you can use the tool to build metamodels that look like this, but you don't know yet whether they adhere to this precise definition. So now I extend this with an embedded Prolog engine, where I just simply take these rules here, I write them down in Prolog, I load them into an embedded Prolog engine, and then I have a translation logic which takes the model in GME and translates it onto these ground terms, loads in the definition of this, the precise definition of the metamodeling language in Prolog, and then runs the proof to see whether or not this metamodel in GME conforms to this precise definition. So what you get is you get a combination of a tool that's very mature, has a lot of features, and you link it with a theorem prover, and you merge these two sides together. And then you can model in GME, you can use all of its features, but you can also check to make sure that what you did exactly adheres to the precise definition. Okay. Now, of course, we don't want to just build metamodels and check whether or not they're right. We also want to implement the metamodeling semantics, which generates a new domain that you can model in from the metamodel. Okay, so now the next step is to define this. Let me go back. The next step in that process, now we have this. We want to define this now, this encoding of domains structurally, so that we can then say that how you map from a metamodel to a domain. Okay, and this isn't incredibly interesting, so maybe I'll go by it quickly. Basically, all you need to observe is that, of course, it's not so hard to make a language that lets you describe structurally horn clauses. All you need to do is define a domain that has some symbols. For example, a symbol definition XYZ allows you to declare that in a particular signature, you have a particular function symbol of a particular arity. So if I wanted to write this signature structurally, I could write it as a set of definition terms where inside these terms are constants. This says that the function symbol f of arity 2 is in epsilon. This says that function symbol g of arity 1 is in the constraint signature epsilon sub c. Okay? We need a symbol that allows us to represent the application of a function to a set of constants. So we have a map symbol where the integer, the subscript, denotes the number of arguments. So here you can just write this in prenix form, basically. And then you basically need a couple things to connect together heads and tails.
So what is the maximal arity for the domain of domains?
That's an important technicality, is that it, again, needs to be finite. You choose some maximal number. But in practice, this isn't too much of a restriction because most languages don't have relations of arity 1,000 or something like this. So usually, I think I extended it to 6, and I haven't run into any problems. Yeah, but that's a good question. Okay, so finally, you need to represent variables, but more importantly, you need a way to represent a clause, and so it's divided into two parts: an axiom symbol, which denotes the head of the clause, and then multiple tail symbols that add on the tails of the clause. And you add on tails by giving some unique identifier to the pairs of, or the axiom and then the associated tails. So this is just some unique identifier you choose from the alphabet. And then you have some rules to make sure that you don't reuse identifiers. Okay, so then you can just encode domains. And you can define a structural induction that says how you get from a domain, which are these two signatures in a set of axioms, to these terms. And I won't go through all of this. It's not that deep, really. But it's not so hard to see, in fact, that this, when you go through it, that this defines an isomorphism. So you have an isomorphism between this. You have an isomorphism between this triple of two signatures in a set of constraints and a set of these terms. Okay, so now you have this part defined. And all you need to define now is this transformation that goes from a metamodel to these terms. And I should say that if you have a set of terms like this, I have a conversion operator implemented that will do the inverse. So if you have a set of terms, it will generate for you the actual domain definition. And it will actually either give you this in Prolog or in a more in a tool neutral format, a mathematical format. Okay, so let me just quickly sketch how the transformation might work. For, let's say, the classes, attributes, association classes, you basically, in the metamodel, you want to introduce a function symbol in the associated domain. So if you define class that's name is x, you transform this to the term definition in the signature epsilon, have a class x of arity 1. Why do I know it's arity 1? Is because that's how I define the metamodeling language. If you define, let's say, an attribute that is associated with class x and has name or an attribute named x on associated with class y, then you interpret this to be an attribute of arity2 that takes its name and its value. Okay? Associations have more arities because they link together two classes, for example. Here's an example. What's that?
Converge within.
Oh, okay, yeah. Okay, so an example transformation you can see here is that you go from a model, a metamodel, you describe it as a set of terms, you apply the transformation, you get this set of terms that encode the domain, and then you just apply the inverse, and you get the precise definition. Okay, and then this has been implemented too in a similar way, that you have the metamodel of the simple metamodeling language in GME. You construct a GME metamodel, and now another extension loads in an embedded Prolog engine. It loads in the transformation, and it runs a forward chaining procedure to get all of the definition terms. It inverts those terms and outputs the precise definition of your domain. Simultaneously, it generates a GME version of your metamodel that you don't know how closely it links to your formal definition, and it generates a tool that can read in the formal definition of your domain and check it in GME. So it basically completes the whole cycle for the user. And I should mention that constraints you can annotate directly into the metamodel, and it as these horn clauses, and it will just add it into the generation procedure. So here's an example when I run the tool on this metamodel here. This is the input metamodel seen as ground terms. This is the resulting the result of the transformation that gives you this in the horn domain, and then it can write this out as a Prolog file. It generates a GME equivalent of this metamodel, and it attaches a well-formedness tool into GME. Here's some of the Prolog that it generates, and it attaches a well-formedness tool into GME so that if you build a GME model and then you check it, it will prove against the formal definition that it generated whether or not this model is well-formed. In this example, this model is not well-formed because I added in a constraint that said that if you have an input and an output, you can't short them. And in this example, it caught that constraint. So the idea then was to be more precise about the mathematical framework that underlies the structural semantics of model-based design. And then to show that in a tool-independent way, you can define this process, and you can inject this process into existing metamodeling tools in such a way that it's fairly transparent to the user. I've described the details to you, so it doesn't look very transparent. But from the user's perspective, again, they build a metamodel, they click a button, and basically all the precise artifacts are generated and then hooked back in for you automatically. You just click the toolbar buttons, and if it says your model is bad, then you have to fix it. And that's basically it. What I haven't had time to talk about, which is also an extensive part of this work, is the constructive theorem prover formula that I've been working on. And basically what you can do with formula is take these definitions that it generates of domains and then have it construct models that satisfy certain properties. If you notice earlier on, a lot of the properties that you want to prove, for example, domain equivalence or structure-preserving maps of transformations, you can all prove them by finding the existence of a particular model that breaks the property. So with a constructive theorem prover, you can prove these properties by asking it to construct a model that would break the property you're trying to prove. If it can't construct such a model, then it's a witness that the property holds. That's basically how it works. And that's the end.
So the witness is the proof?
Yes, it's the actual model. So what this does is it actually constructs a set of terms that would satisfy the property. So if I want to say are two domains equivalent, I would say find a model that's in this domain and not in that domain.
Yes, but if they are equivalent, then you get a proof that they are equivalent.
The proof is that there exists no model. That's the proof.
Okay.
Yeah.
And so how is it constructed? So it's constructed in the sense that it produces a model, or is it constructed?
Yeah, in the sense that it produces a model. Yeah.
Okay.
Yeah. So if you phrase the let's say the contrapositive or something like that, and and what you're looking for is for it to not find a model, then that's what it will do. It will not construct a model for you. But for example, in domain equivalence, if it finds such a model, it's usually the model that disproves it that you're interested in, because that shows you the model that's in one and not in the other. Yeah. So.
Well, it transited to the question phase. More questions? How new was it in your community?
So this work I just presented at the MSoft conference, the Embedded Systems Conference, which is the main embedded systems conference, and it was well liked, and fairly confident that this is quite new. So a lot of the work has been done on the behavioral semantics side, looking at different process calculi or extensions to hybrid systems. So a lot of work has been done on what are the semantics of domains, the behavioral semantics of domain-specific languages, but not so much on how do you really talk about the structure. And work that I've done after this actually is aimed at looking how structure and behavior link together. And there's some interesting things to be said about that.
But here everything is discrete and digital, no continuous stuff. Or within a model there could be something continuous, right? If it's a function.
Right. Yes.
It incorporates it inside.
Right. So you can have a structure that under a particular interpretation maps to something continuous. You could say that, I don't know if it's anything worth saying, but if in sigma you put the reals, you have a lot of models. I don't know if you'd call that continuous or not.
Yeah. And what was the connection to this synchronous languages?
Oh, the connection to synchronous languages is so. From my presentation on synchronous languages, you remember I approach the synchronous languages by dividing them into pieces, several pieces, and the pieces interact with each other. And it turns out that that the reason why this works, why you can divide it into these pieces that interact in such a nice way, is because the structure and the behavior of these pieces are related in a very nice way. So that's how, in the end, it relates. Once you understand how you can formalize structure, you actually see that there's a very interesting link between the sort of models you build and the way that you interpret those models. And when you understand that link, you can prove why this separation into pieces works and comes together nicely. Yeah.
Thank you very much.
Thank you.